A deep dive into scikit-learn decomposition, unraveling the secrets of dimensionality reduction. Scikit-learn's decomposition module offers a powerful toolbox for dimensionality reduction techniques, allowing us to distill the essence of high-dimensional data while preserving its core information. This module focuses on methods that decompose the data into a set of components that capture its inherent structure, effectively reducing its dimensionality without sacrificing too much information. Understanding the core concepts. Dimensionality reduction: the art of transforming high-dimensional data into a lower-dimensional space while minimizing information loss. It simplifies analysis, improves computational efficiency, and enhances model performance by combating the curse of dimensionality. Components in decomposition. These are the new axes or features that represent the original data in a lower dimensional space. They often capture specific patterns or directions of variance in the data. Explained variance: the amount of variance in the original data explained by each component. Higher explained variance indicates a component capturing more of the data's essential information. Eigenvalues represent the variance along each principal component. Larger eigenvalues signify components that contribute more to the overall variance of the data. Eigenvectors: these are the directions of maximum variance in the data, which are represented by the components. They act as the basis for projecting the data onto the lower dimensional space. Deconstructing the methods. 1. Principal component analysis (PCA), the workhorse of decomposition. PCA identifies the directions of maximum variance in the data and projects it onto these directions, forming new, uncorrelated components called principal components. Key features. Linear transformation: PCA finds a linear combination of the original features to create new components. Variance maximization: it aims to maximize the variance captured by each successive component, ensuring that the most significant patterns are preserved. Orthogonal components: the components are orthogonal, meaning they are uncorrelated. Applications. Data visualization: reducing high-dimensional data to 2D or 3D for visualization. Noise reduction: by removing components with low variance, it can filter out noise in the data. Feature extraction: extracting the most informative features from the data, useful for improving model performance. Implementation. sklearn. Decomposition. PCA. Parameters. N components: number of components to keep. SVD solver algorithm used for singular value decomposition (SVD). Whiten whether to standardize the components. 2. Non-negative matrix factorization (NMF), a technique that decomposes the data into two non-negative matrices, capturing parts-based representations of the data. Key features. Non-negative values: all elements in the decomposed matrices are non-negative. Additive representation: NMF finds additive parts that constitute the data, allowing for interpretable components. Applications. Topic modeling: extracting topics from text documents. Image analysis: decomposing images into basic building blocks. Implementation. sklearn. Decomposition. NMF. Parameters. N components: number of components to keep. Init initialization method for the factorization. Solver algorithm used for the factorization. 3. Truncated singular value decomposition. Truncated SVD, a variant of SVD that only computes a subset of the singular values in vectors, achieving dimensionality reduction. Key features. Similar to PCA, truncated SVD is closely related to PCA. Faster computation: it is computationally more efficient than PCA, especially for large datasets. Applications. Large-scale data analysis when PCA is too computationally demanding. Recommender systems extracting latent features from user item interaction data. Implementation. sklearn, decomposition, truncated SVD. Parameters. N components, number of components to keep. Algorithm used for SVD. 4. Sparse principal components analysis. Sparse PCA, a variation of PCA that promotes sparsity in PE components, resulting in more interpretable and potentially more robust representations. Key features. Sparsity encourages components to have only a few non-zero elements, making them easier to understand. Interpretability. Sparse components often correspond to specific features in the data. Applications. High-dimensional feature selection, selecting the most relevant features from a large number of candidates. Understanding complex data, identifying the underlying structure of complex and sparse datasets. Implementation. sklearn, decomposition, sparse PCA. Parameters. N components, number of components to keep. Alpha controls the level of sparsity in the components. 5. Independent component analysis. ICA aims to find a set of statistically independent components that underlie the observed data. Key features. Statistical independence. ICA seeks components that are independent, meaning their joint distribution is the product of their marginal distributions. Linear mixing. It assumes that the observed data is a linear combination of independent sources. Applications. Signal separation, separating mixed signals, such as in audio or medical imaging. Blind source separation, separating unknown sources from observed mixtures. Implementation. sklearn, decomposition, fast ICA. Parameters. N components, number of independent components to extract. Algorithm used for ICA. Choosing the right method. The choice of decomposition method depends on the nature of the data and the specific goal. PCA, a good starting point for many tasks, particularly when seeking a linear variance maximizing representation. NMF, ideal for non-negative data and scenarios where interpretable paths-based representations are desired. Truncated SVD, a computationally efficient alternative to PCA for large datasets. Sparse PCA, excellent for promoting sparsity and interpretability in the components, especially when dealing with high-dimensional data. ICA, suitable for finding independent components, particularly when dealing with mixed signals or blind source separation problems. Beyond decomposition. While sklearn, decomposition offers powerful tools for dimensionality reduction, it's crucial to remember that it's just one part of the data analysis pipeline. Other techniques, such as feature selection and manifold learning, can also be employed for similar goals. Conclusion. Scikit-learn's decomposition module provides a versatile set of tools for dimensionality reduction, allowing us to extract meaningful information from complex datasets. By understanding the strengths and weaknesses of each method, we can choose the right approach for our specific needs, enabling us to gain deeper insights from our data while simplifying analysis and improving model performance.